Hello friends, welcome again to the tetrahedron chemistry classes. So in today's class I am going to discuss a very important method in organic synthesis, in fact reaction in the organic synthesis, which is your epoxide ring opening, because this epoxide actually gives the variety of the functionality in the organic synthesis, right? So this is a very important reaction, and we will see how we can open this epoxide ring with the help of the variety of the reagents. I'll try to cover as much as reagents which I can cover today, okay? And there may be a chance that one or two or few may be left, you can go through by yourself, okay? But I'll give you the maximum information about the epoxide ring opening today. So before going into the details of the epoxide ring opening, you should know what is epoxide. Epoxide is nothing. You see here it's a three-membered ring, okay, heterocyclic ring it is, and it is having the oxygen. So if you count this oxygen as 1, this is 2, this is 3, okay? And don't forget, your oxygen will always have 2 lone pair over there. So it is a cyclic ether. It is nothing but it's a cyclic ether. And remember, this oxygen is electronegative, so what can happen, this can pull electron density towards itself, okay, rendering these two carbons positively charged. So there are two positive charges on the two carbons, that is carbon number 2 and the carbon number 3, okay? So which makes these carbon 2, so I am writing C2 and C3. So these two carbons actually are what? They are electrophilic in nature. They are electrophilic in nature due to this positive charge. Hence, or you can say that therefore, they are prone to attack by nucleophile. Prone to attack by nucleophile. This is something very important which you should know. And one more thing, this three-membered ring is actually, you see, very strained ring. It's a three-membered ring and it is strained, okay? So whenever this much of a strain or the strain is there in the molecule, so it's try to open itself by releasing it tries to actually removing its strain by releasing the ring, okay? So this is actually very susceptible towards the nucleophiles. So if you put any nucleophile over there, okay, so it will readily open in that manner. See, this is negatively charged, so what can happen, this nucleophile can attack on any carbon because it's a symmetrical ether, so symmetrical epoxide, so it can attack either 2 or 3. It will not make any difference in the final product. So what will happen when this nucleophile will attack here, so this bonds gets broken and the oxygen pair shifts here. So what you left with, actually you left with this nucleophile which is added to the carbon number 2, okay, and then you are having your carbon number 3, and this carbon number 3 is having the oxygen which is now negatively charged. And if you do the protic workup for this one, okay, I can write protic workup, I can put positive over there, then it will result in the product that is nothing but your alcohol type of the compound. So this is how you can get this one, okay? So since I have I am talking about the nucleophiles, so variety of the nucleophiles which can attack on the epoxide ring. Say you may do this reaction in basic condition, okay, and you may use the hydride reagent, and the source of the hydride could be anything, right? You can use your sodium borohydride, okay, or you can use your lithium aluminum hydride. I am writing LAH. You can use your dibal, okay, and you can use your, say, most reactive hydride, that is sodium hydride, okay. So these are the sources of the hydrides, and along with the hydrides you can use cyanides in that case. They are also nucleophilic in nature. You can use your amines, you can use your alkoxide, you can use your alkyl silane, you can use your Grignard reagent, okay, and variety of organometallic reagents you can use. Okay, so since all these species you can see here, they are negatively charged, so they can easily attack on the alpha carbons of your epoxide. This is something very important which you should know. Okay, now say for example, like say I am having say some symmetrical or unsymmetrical ether. So I can write here, say I am having unsymmetrical epoxides. Unsymmetrical epoxide. So how this unsymmetrical epoxide opens? What would be the regioselectivity in that case? Okay, so say I am doing the reaction in the basic medium. I am doing the reaction in the basic medium. For example, you have taken sodium hydroxide. Okay, so this sodium hydroxide, you know, it will liberate hydroxide ion OH negative, which is nothing but your nucleophile. Okay, and say you are having some ether, say you are having this ether, this is your 6-membered ring. Okay, and this is oxygen, this is oxygen, so this is epoxide. Okay, and of course this is your methyl group, and then you are having here hydroxide. So what I can do, I can straightforward write hydroxide in that manner. Now you have two options, whether your this hydroxide attack on this carbon or it may attack on this carbon. So if you call it as carbon number 1, so oxygen number 1, carbon number 2 and carbon number 3. So you are having the two options in that case. So what can happen, say for example I am following this say this is the path A, this is the path B. So right now I am following path A. Okay, when I am following the path A, what will happen? You will have the resulting species which would be just like that, a 6-membered ring. Okay, and you know, when this you see, when this hydroxide will attack over there, one of the bond between carbon and oxygen will break and the electron density will shift towards the oxygen, which is the more electronegative element in that case. Okay, so this will shift in that manner. So the moment it will shift, it will result in a compound. See, there is CH3. Okay, and then this part is having your OH group, and then you are having oxygen 1 2 3 4 5 6. Now one negative over there. Okay, and after that if you do the protic workup for this one, right, if you add positive, see there may be the various source of the proton. See, for this proton you may straightforward write the acidic workup or the protic workup, or you may put some acid like H3O positive. You may have your water also, and you may also use the ammonium chloride. Anything you can use in that case. Okay, so what will happen in that case? It will result in the product, and that product would look like just this. So CH3 is here and OH over there, and say this is OH again. So basically you have produced your diols. Now what about the stereochemistry of the diol? Say for example I have started my reaction in that manner. Okay, say this is your beta bond. See, from the basics of the stereochemistry, you know the beta bonds which are shown by the solid wedge, they are actually above the plane. Okay, so you can say here whatever I have drawn these two bonds, they are above the plane, they are in the beta position. Okay, so what will happen when this will attack here? So this intermediate actually, because see, since this epoxide is actually above the plane, so this has to attack from the bottom of the plane. alpha position. It will attack from the alpha position. So for your understanding, I can write alpha attack. Okay, however, this terminology you will not find in the textbook, but I am explaining you. That means it will above, below the plane. Alpha attack means below the plane. Okay, so when it will attack below the plane, so what will happen? You see, in the final product, it will also remain in below the plane. Okay, and this I have already told you was above the plane. Okay, when you do the protonation, so what will happen? This would remain below the plane and this will come up above the plane. So basically you have produced the diol. Okay, and in this diol you can see this is your beta alcohol, beta OH, this is your alpha OH. And what important thing which you are observing here at C2, so if I can write this as 2, this as 3, so at C2 inversion of configuration actually occur. Inversion of configuration. This is something very, very important. Okay, and you know that this inversion of configuration is basically the specialty of your SN2 reaction. So this actually also indicates that this reaction proceeds via SN2 mechanism. So this reaction is having the characters of your SN2 reaction. This is something very, very important. Okay, so this was the path A. Now if you follow the path B, say for example if you have followed this path B, so now what I can do, I can write the path B here. So in the path B you will have your product in this way. Okay, this was your CH3 and hydroxide attacked from the bottom, so this would be OH. Okay, because see the moment this will attack there. Okay, so this electron density will shift over here. This is the second pathway of the reaction. Okay, and at this position you are having oxygen with negatively charged. So if you do the protic workup, like if you put the H positive over there, then your product would be CH3 in the plane, this OH below the plane and this OH above the plane. That means it is beta and this one is the alpha. So you are having two products. Say this is product A and this is the product B. Okay, now the question is that which one would be the major product in that case? So remember, in that case, whenever this attack will occur, your nucleophile, whatever the nucleophile you are taking, like in that case you are taking this hydroxide as a nucleophile in the basic medium, it will always attack from the less hindered positions to avoid the steric effects or the steric crowding or the steric repulsion. So this path is the more preferred pathway because it is less sterically hindered, because only one hydrogen is there, while in the above case there is a methyl. This will actually crowd this carbon number 3. So this pathway B is not a very good pathway. Okay, but this pathway A is a very good pathway because it is less sterically hindered. So in that case, that would be, this A would be your major product. Okay, and this B would be your minor product, and this will always happen whenever you have the asymmetrical or unsymmetrical epoxide. Okay, this is how you can go through. Now we can see the reaction in the acidic medium also. So what I can do, I can write here acidic medium. We are following the reaction in the acidic medium. So what can happen in the acidic medium? So whenever I write the acidic medium, say for example I am having say this epoxide, like I can write in that manner. So this is oxygen which is over there. Okay, and this is the hydrogen. I can write this as alpha and this is beta. Okay, and you see here this is the methyl group, and in that case another methyl group is also there. They are alpha and beta, and 2 lone pairs are there. Okay, and then you are having, say, this time you are having the acidic medium. So what is the meaning of the acidic medium? You are having the H positive. Now since you know these 2 carbons actually, right, say this one is slightly positively charged, this is also positively charged, oxygen due to the electronegativity is negatively charged. So what can happen actually, this H positive can attack on the negative side, not on the positive side. So what will happen, the electron pair grab this proton, and the moment the electron pair grab this proton, you will have your product in that manner. See, it will grab this one. Now you have 2 options, right? So first of all, see, since this in the acidic medium, actually the reaction follows the SN1 pathway. Okay, and you know in the SN1 pathway you are having the carbocation. So in that case you can form the carbocation. So in first case, what I am doing, I am shifting the electron density. See, the moment it will grab this one. Okay, so this bond actually gets broken and the electron density gone there. So in that case you will have, okay, this is your methyl CH3, this is your another methyl CH3, this was your hydrogen, and this was your another hydrogen. This is how, okay, and then you are having this O with hydrogen. Okay, now it is positively charged. Now this carbon actually is trivalent only. When it is trivalent, that means it is positively charged. Okay, and it is a carbocation, and this carbocation is, you know the nature, it is 3-degree carbocation. Okay guys, it's a 3-degree carbocation. And you may also follow the other pathway. Say for example, when this has grabbed in that manner, so electron density, for example, say shifted here. So if I call it as pathway A, okay, then this would be your pathway B, right? So I can write B over there. So whenever you have this pathway, then what will happen in that case? Your oxygen will remain in that case, right? And this is your methyl, and this is your another methyl. Okay, and these are the 2 hydrogens over there. You can write hydrogen, you can write hydrogen here. This is hydrogen again with positive. Okay, now again it is carbocation. You see, this center is carbocation. Like in the previous case, you are having the carbocation at the left hand side. Now you are forming this carbocation at the right hand side. So what can happen? You can put positive over there. So the moment you put the positive over there, it is again a carbocation. But remember, this carbocation is 1-degree carbocation. Okay, so you know this would be the more stable one. This would be more stable. Okay, and this would be less stable. Okay, from the basics of the organic chemistry, you know these things. So how the reaction actually proceeds further? So in that case, what you can do, you can take any nucleophile, right? Say for example, if I am doing the reaction in that manner, so what I can do, say not this one. Okay, so I will need this in the later stages. So what I can do, okay, forget about this, I can draw it in the another manner. Say for example, in that case, now you have proceed your reaction with, say, methanol. This is CH3, this is OH. Okay, 2 lone pairs are there. So this can attack at this position. So the moment it will attack at this particular position, okay, in the tertiary carbocation stage, so you will have your product in that manner. Sorry, I'll use the different color for this. Say this was the methyl CH3, this is another methyl, and now this is having OH and CH3, which is positively charged. Now how it has happened? You see, this lone pair actually is consumed. by this carbocation to form a bond, so definitely it would be positively charged. Okay, and your next part, say I am removing this one. Okay, this part will having your hydrogen usually, which was already there in the mixture. So this is O, this is H. Okay, so this is how you can write this one. Okay, so this is something very, very important which you need to understand. Okay, so now this is OH, this is OH, and in the last stage what can happen, this hydrogen, actually you have used this acidic medium in that case. So for example, you have used H2SO4, so you left with this HSO4 negative. So this actually will grab this proton and the electron density will shift over the oxygen and you will have your product, and your product would be like that: your methyl, your another methyl, and then your O CH3 along with this, with these two hydrogens and another hydrogen here, and then you are having the OH functionality. So basically this is your product. Okay, this is your product, and this product would be the major product since it has produced from the tertiary carbocation. Similarly, if you form the product, see if you form the product from this this one, so it will give you the another product which would be the less stable one. So I am drawing the structure only, you can work by your own. So it would be your OCH3 and two of the hydrogens. Okay, and then you are having the OH. Okay, and then the methyls. So this is Me, this is Me again. So this one would be the minor one. So you can work for this by your own. So this is how in the acidic medium goes. So it is very important to remember, if you are using in the basic medium, it will follow your SN2 type of the mechanism, and in your acidic medium it will follow your basic your SN1 mechanism. Okay, so this is something very, very important which you need to understand. I hope this is clear to you in the basic medium as well as in the acidic medium. Okay, so now another reagent which we can use in that case, say for example we are having the reaction, say same epoxide I am taking. Okay, so this is CH3 and this is oxygen, this is oxygen. Again I am taking the beta. So beta means they are above the plane. So in that manner, okay, you can write. Okay, and then say your reagent is Grignard reagent. Okay, so I can write CH3 MgBr, and you know in that part this carbon is negatively charged and remaining part is positively charged. So what will happen, this methyl or this nucleophilic part will attack on these this is carbon 2, this is carbon 3. So again it will attack from the less hindered side, so major attack from this particular part. So I am only going for the major product, and you can go for the minor product also by doing the reaction by your own, but it is important to note that the nucleophile will attack from the less hindered side, so it is attacking from this particular end. So what will happen in that case, you will have your product, or not product, actually you are having your intermediate. This is the 6-membered ring having this is CH3. Okay, and this is then when it is attacked here, obviously the electron density will get shifted over there, and so this will have this oxygen with negative charge, and since it has attacked from the bottom side, so it would be alpha, right, and this alpha will have the CH3 in that case. So if you do the protic workup, okay, I am writing H positive, source could be anything, ammonium chloride, acid, or the even water can do the reaction actually. Okay, so again you see, if you draw this one here, okay, so this is CH3, this is OH, and this is your methyl. So again you see this bond, actually you see here this bond was beta earlier, but in that product this bond is alpha. So you are observing inversion of configuration at carbon number 2. That means the reaction proceeds via SN2 mechanism. This is the inversion of configuration. Okay, so this is the major product. What you can do, you can attack this from here also, and you can also think about the minor product in that case. You can draw the reaction mechanism by your own. While in the earlier case, you can see here when I have drawn this in acidic medium. Okay, so in acidic medium you can see here, you see this was actually your carbon 2, this was your carbon 3. So in that case, actually if you carefully focus on this one, there is no change in the stereochemistry on the product, it will remain same. So because in the see in SN1 mechanism, carbocations are formed, and these carbocations are planar in nature. When they are planar in nature, so there is equal probability of attacking from either side. Okay, so in that case there is no inversion. Okay, while in the basic medium, you are having the inversion at C2. Okay, you can see here inversion at C2, while in case of the Grignard reagent also you are observing at C2 this inversion of configuration. So this Grignard reagent may also be used. Okay, so this is something very, very important. Now what other reagent we can use? Say for example, I am having another reaction. Say this time you are having, say, this epoxide. So this is oxygen. Okay, and this is the beta bond, say, right, this is the beta bond, and here you are having the substitution of, say, CH3, and here you are having, say, this phenyl substitution. I am going to pH for this one. Okay, and again you are having the CH3. Say for example, this is the product, this is the epoxide starting, okay, material, and then you are having, say, your reagent, say lithium, and then this triple bond and this one. So basically this is your alkyne derivative of lithium, and you know this metal is positively charged. Okay, then definitely the carbon which is there, say you can see this is carbon number 1, this is carbon number 2, this is carbon number 3. So this carbon number 1 is negatively charged. Okay, so it is again a nucleophile. So this nucleophile, what it can do, it can attack. So obviously it will attack on this particular carbon, right? Say if it is 1, if it is 2, if it is 3, so it will attack on carbon number 2. Why carbon number 2 it is attacking? Because it is having only one methyl group which is less sterically hindered. So nucleophile will always attack from the less sterically hindered side, while in the carbon number 3 you are having this substitution, right, pH, CH2pH, and you are having the CH3 substitution. So this is actually more crowded, so it is not easy for this nucleophile to attack from this one. However, you can go for the minor product also by doing the reaction by your own. I am showing only the major product in that case. Okay, so what will happen when the reaction goes? You will have your product. So this will attack in that case, and the electron density will shift over there. So what will happen? You see this is CH2pH, this is CH3, and this is your alpha oxygen with negative. Okay, this was your CH3, and now this is having this system. Okay, so this is, since it has attacked from the alpha sides, you see here I can write it as alpha attack, that will attack from the bottom side. So this will form a bond from the bottom side. Okay, and you know, if it is the carbon number 1, so this would be your carbon number 2, and this would be your carbon number 3. Okay, this is how you can write 1, 2, 3. So earlier in that case you are also having, say, 1, 2, 3. Okay, you are having the 3 carbons only there. Okay, So did I miss? Okay, you are having 4, I think. 1, 2, 3 and 4. Sorry. So this is 1, 2, 3. So there would be one more bond, which is 4. Okay, this is how you can write. And then if you do the protic workup for this one, right, say for example if you use the ammonium chloride, in that case, you know, ammonium chloride will produce the ammonium ion, and this ammonium ion, actually the hydrogen from this ammonium ion would be grabbed by this oxygen, and it will result into your final product. That final product would be your pH. This is CH3 carbon, and this OH would be the beta, this would be the CH3, this is the alpha bond, okay, and you see this is actually triple bond carbon, just like that. Okay, 1, 2, 3 and 4. So again, if you focus on the reactions, it was 2, it was 3, inversion of configuration at actually C2. So whenever you actually do the reaction with the nucleophile, very strong nucleophile, you will have this kind of possibility. You can have this kind of the reaction. Again, this is something very, very important. Okay, now moving to the next method, what other reagent we can use for this one. For example, you are having this epoxide, say just like that, I can draw. Okay, say this is your epoxide, which is beta. Okay, what I can do, I can put oxygen over there, and say you are having cyanide. In that case, it can come from anything. It can come from the KCN, it can come from the NaCN. Okay, so again you see this will attack, this nucleophile will attack. See, this was your carbon 1, this is your carbon, see this is actually 1, and say this is 2, this is 3. So again this will attack here at this carbon. Why? Because it is sterically less hindered. Okay, when it is sterically less hindered, it will facile this attack. It is the alpha attack, and when this will attack here, so what will happen? The electron gets bond gets broken, and the electron density will shift over the oxygen. So what product or intermediate you can have? Just like that. Okay, I can write oxygen with negative here. This was 1, and you see cyanide is attacked over there. Okay, so basically it's a 3 carbon system. This is 2, 3, and you can call it as 4. So it is just like that, 2, 3 and 4. So this numbering is not according to the IUPAC nomenclature, but for your understanding I have given the numbers. And then say you are having this methanol, you are doing this reaction in the methanol. So what can happen? This oxygen can grab hydrogen from there. Okay, and when it will grab the hydrogen from there, this will give you the product. So the product would be, say, cyanide in that case, and this would be the OH. So this is your product. So variety of the reagents you can use in that case. Okay, similarly what you can do, I am leaving this up to you. You can also use, say, NaS pH. So sodium is positive, rest is this part. So this is actually your nucleophile. So you can do the reaction by your own to get the product. Okay, so this is how you can write. Say you are having the epoxide, writing in that manner, and you have been given these reagents, NaSPH1, and number 2 is, say, H3O positive. So what product you will have, you can do the reaction by your own. And similarly guys, you can do the same reactions. For example, you have been given this epoxide, right? Say this is methyl, and now I have changed the stereochemistry a little bit. I have put it oxygen over there. So in that case, your nucleophile will attack from the beta side, that means above the plane, because this dashed badge is below the plane. And say you are using in that case NaN3, sodium azide. Okay, and sodium azide, after sodium azide you are using say some H positive. So what would be the product in that case? You can go through, okay, because this is positive, this is negative, so this will attack now in that case, okay. So it will attack, how it will attack, you see here, this N3 negative will attack from the beta side, so this would be above the plane in that case. You can draw the product by your own. So this is something very, very important. So I cannot cover all the aspects here because the length of the video will go very, very high, okay. So I have to finish it in 1 hour or say 1 hour 15 minutes. So I am leaving some of the questions for you only. Say now you are having the next problem. Now it's very important, special case. Special case, epoxide opening with HBr. Epoxide opening with HBr. Okay, how the reaction goes? Say for example, I am giving you this thing. Say you have been given this epoxide. So this is your CH3. There is no stereochemistry shown here. This is the epoxide, and then you are having your HBr. So HBr means you are having acid, H positive and this is negative. So delta positive and delta negative. So since it is negative, this hydrogen is actually your positively charged. So the lone pair present on the oxygen will grab this proton and it will give you the intermediate, and that intermediate actually would be like that. This is CH3, okay. This is OH. Now the bond will remain as such. This is lone pair and positive charge on the carbon. Say you are having this one, okay. Now in that case, what would be the expectation? See, now the expectation would be like that. It can form the carbocation. So how it can form the carbocation? Say in the path A, I am taking, this is the path A. So in the path A, what actually has happened? This has removed here. This will move here. So you will have this carbocation, CH3. This carbon would be positive, okay, and then you are having OH. So this is the carbocation which you are having, and then you are having another carbocation. I am using the different color for this one. Say you are following the path B. So in the path B, say this bond actually gets broken and the electron density shifts here. So this is the path B. Earlier was the path A, okay. Then again what will have? You will have the carbocation in that case, and that carbocation would be, say for example, this is CH3, okay, and say this will have the OH and a positive charge here. Again this is carbocation, but you know this carbocation is 3 degree and this carbocation is 2 degree. So if you summarize the product, okay, how you can summarize the product? You are having this Br negative now in both the cases. Here also you are having the Br negative. So this Br negative will attack here and this Br negative will attack here. So what would be the product? So in the first case you are having the product just like that. So this is CH3, this is Br, and then you are having the OH, okay, and then again you are having the product here. This is CH3, okay, this is OH and this is Br. Since it has produced from the tertiary carbocation, okay, so this actually would be the major and this would be the minor, but in actual reaction the opposite things here. So experimental findings are little different. In the experimental finding, this actually is the minor product, okay, and this one is the major product. So this is the exception which you can attack, which you can think about. So what is the reason of this exception? See, in that case you see here, when what happens, this intermediate is formed, okay. So this Br negative which is there, actually it approaches towards this intermediate before the formation of the carbocation, okay, and this act as the nucleophile and it will try to search the position which is actually less sterically hindered, so it will attack from here. And when this will attack from here, so this follow this particular path and this becomes major. So in that case, though it is an acidic medium, but it follows the mechanism just like your SN2, not SN1. Okay, it is not following the SN1 kind of the mechanism in that case. The reason is quite clear. Br negative, which is this one, is a very powerful nucleophile. So this before the formation of these carbocations, actually this Br approaches on this intermediate and it attacks from the less hindered side to produce this particular product. So whenever guys you see HBr is there in the epoxide opening, so you will actually try to follow your SN2 mechanism, and you will have the compounds, or the say you are having the products in the opposite manner, like major become minor in that case and minor become major. So these are the certain things actually which you have to keep in mind. So now I am going to the some more specific problems which you should know. Say you are having some epoxides which are conformationally rigid epoxides. So what is the meaning of the conformationally rigid epoxide? Say you are having this, okay, just like that, you are having this one, okay, and here you are having the epoxide linkage. So stereochemistry is beta type, so it is above the plane, and here you are having this tertiary butyl group, and you are doing the reduction. Say for example you are having the lithium aluminium hydride, so you are having H negative here, and source is lithium aluminium hydride. So in that case you see here this can attack. Okay, how it will attack, this is something very important. Okay, so since actually this H negative is there, and this epoxide is actually your beta epoxide, so this should attack from the bottom. Okay, so when it will attack from the bottom, so how it can attack, it can attack here actually. Okay, when it will attack here, the electron pair will get shifted over there, and when this will shift, you will have your intermediate, and that intermediate would look like, say this one, this is your tertiary butyl group. Okay, and this hydrogen hydride has attacked here, and of course this would have oxygen with negative charge, and the stereochemistry would be like that. This H which attacked here actually, this actually below the plane. This is something very important which you should know actually. However, it is not important to show this one. Now in the next case, say for example if you do the protonation of this one, say the protic workup, so this will grab this, and when it will grab this, then you will have your product in that manner. Your oxygen hydrogen, that is alcohol, which is beta, and sorry, so there is no problem in that, so I can move the substituent. So both are same actually, this okay. So you are having this particular product. Now the important thing is that how actually it had happened. So remember, whenever you have this 6-membered ring, your hydride or the nucleophile will attack axially from the axial side. So if you draw the 6-membered ring for this one, say for example for this one I am drawing the 6-membered ring just like that, just like that. Okay, and this epoxide is actually your beta, so you can draw epoxide just like that. Oxygen, why I have drawn this in that manner, because this is beta, that means above the plane, so I have shown this epoxide as above the plane. Okay, and the next position, which is this one, is having your, say, this tertiary butyl group. Okay, and you know that this tertiary butyl group is a very bulky group, it will automatically occupy the equatorial position, it cannot go to the axial position. This I have explained in my stereochemistry lectures actually. Okay, so you can go through and search the stereochemistry lectures in tetrahedron chemistry classes. Okay, and say now what can happen. Say you are having the hydride. This is H negative. Okay, this is H negative. Then the source, you know, this is LaH, lithium aluminum hydride, and you can use the sodium borohydride also. Okay, so how it this can attack? For example, this is attacked from here. Okay, when it will attack from here, what can happen? Or see the correct way of showing this one. Since I have already told you it is your axial attack, so I cannot draw in that manner. You see these are the equatorial positions. Right? These are the equatorial positions which are occupied. Okay, so the only chance which actually this hydride is having to attack from the axial side. Okay, so to attack from the axial side, I am putting this H negative here intentionally. Okay, and this will attack on this carbon, and the electron density will get shifted over there. So your resulting species would be just like that. Your 6-membered ring, just like that. Okay, and this is the hydrogen which is attacked. So this will go up, which is negatively charged, and this is your tertiary butyl group. And then if you do the protic workup, say you are having the H positive over there, so this will grab this, and when this will grab this, you will have the product. And what product you can have in that case? The product would be just like that. So this is tertiary butyl, this is OH, and this is H. Okay, so this is something very, very important. So this is above the plane, basically it's beta, and this is below the plane, it is alpha. In the product also you can see this is alpha and this is beta. Okay, so this is how you can form the product actually. Okay, so this is something very, very important which you should know. And of course this product is the major product. Okay, see, in the organic synthesis you have always problem with the parallel reaction and the side reaction, so you will also have the minor product. Okay, and you can draw the minor product also. I am not going to draw that minor product from here, but you can do the exercise by your own. So how you can go for this one? What you can do, you can actually hydride attacking from this position, you can try to attack from this position at the top side. Okay, when it will attack from the top side, then the product would be different. Okay, and the stereochemistry would be the different. Okay, or not stereochemistry, but the positions of the groups would be different in that case. Okay, when it is attacking here, the product would be just like that. Okay, the product would be just like that. I am drawing the product for you, and you can do the reaction by your own. Okay, say this is your OH and this is your this. Okay, so it is always above the plane, remember. Okay, so this is minor product. You can draw this minor product by your own by attacking this on that part. Say by attacking this nucleophile from this side actually. So this will get opened here. So 1, 2, 3. So you have relation 1, 2, 3. So here you see 1, 2, 3 relation are there. When it is attacked from actually this bottom side, electron density gets shifted over there. So relation was 1, 2, 1, 2, 3, 4. So here you see it is having the relation 1, 2, 3 and 4. Okay, this is how you can do the reaction. This is something very, very important. So there are varieties of ways of doing such kind of the reaction. Okay, now say for example, I can give you one more specific, very special example. You can see here what is the special example. Say for example, you are having this system. Decaline system you are having. This is methyl, which is beta, and this hydrogen, which is alpha. Okay, I can write Me here, and here you see you are having this bond. This is the dash bond. That means this epoxide formation is from the bottom of the plane. So this is actually what? Alpha epoxide. And say you are having some species, and that species is HBr. And again, don't forget to apply that. It will behave, it will follow the SN2 type of the mechanism. This is something very, very important, okay, which you should remember. Now I will not draw the mechanism, but I will straight forward jump to the products, and then I will discuss the mechanism of the major product. So what product you can have in that case? So this is your Degarine system, 2 6-membered ring fused. This is methyl up and this is hydrogen down, okay. So in that case you are having this OH up and then you are having this Br. This is one of the product. Second product is, again you see, this is methyl, this is hydrogen, okay, and here in that case here beta, that is sorry Br up and here OH down. Say you are having these two product, okay. So in that case, actually in this particular example, this is your minor product and second one is the major product. So how we can do draw the reaction? For this you have to draw the 6-membered ring, okay, that means the Csir conformation of the given isomer. Say this is just like that, okay. It is not looking very good. So what I can do, I can draw in that manner. Say this is your Csir conformation, okay. So at this junction you are having this methyl, which is this one, okay. I have put it this here actually, okay. And see, this is actually your what, alpha epoxide. So this epoxide will form below the plane. So this is the epoxide linkage, and now this HBr is there. So this will follow the SN2 kind of the mechanism. So what can happen in that case? You are having this Br negative, and this Br negative will attack from the axial side. So obviously this axial would be from the upside, right? Because it is down. See, in the bottom plane you are having this epoxide, right? And you know this oxygen will have the lone pair over there. If this Br try to attack from here, so this is sterically hindered position, okay. So it is better for this bromide to attack from this particular position, okay. So when this will attack from this position, so what actually your intermediate will would be look like that. Say this is the first ring and say this is the second 6-membered ring. This methyl is up and this Br has attacked from the axial position, so Br is up, and when this will attack, so this will get shifted over there. So your oxygen is down, 1 2 3 4 5 6 negative. If you do the protic workup like H positive, then you will have your product just like that. This is methyl, this is Br, this is OH negative. So this actually your major product, okay. How you can draw the minor product? So for minor product you attack from this position, okay. So this will get up, and when you will this will attack from here, so this will go up, this Br will go up. Since this is bottom side actually, right? So Br will attack from somewhere here actually, okay. So this will get up, it is bottom, so this in the attack it will go up. You see in the minor it is up, while see in the major product this OH is bottom. You can see this OH is bottom, or you see the alpha, this is alpha, this is, so I can write it here. This is your alpha, so here also you see this is alpha, this Br is beta, so this is also beta, okay. For this you need to understand the stereochemistry, okay, or the 6-membered 2 Csir forms of these things, right? So this is something very, very important. So where variety of reactions are there in that case, okay. So I can go for one or two more reactions. Say you are having, now I am doing this epoxide opening, and in that case I am having trimethyl silyl iodide. I am having trimethyl silyl iodide. So in that case what will happen? Your epoxides it will form alkene. Epoxide will form alkene. Okay, how the epoxide will form alkene? So I can draw the epoxide. Say this is your epoxide, and this is your tertiary butyl, and this is also your tertiary butyl. Okay, and your reagent is Me3SiI, trimethyl iodide. So what your product would be? Product would be your alkenes. Okay, that alkene would be like that. Okay, so hydrogens are always there, you see here. If you want, then you can draw your hydrogens over there. So this is how you can form the product. So what is the mechanism involved in that case? So for mechanism it is quite easy. Say you are having this Me3, and then you are having SiI. So your silicon iodide bond is there, which is weak bond. See, whenever you are having the silicon carbon bond and silicon iodide bond, your silicon iodide bond is the weak bond. You should remember actually. So lone pairs are there on the oxygen. So this silicon is having the vacant d orbital. So this can attack here on the silicon, and this iodide gets removed from here. So what would be the species in that case, right? So your species would be like that. I can draw the species oxygen, oxygen, and these are the two groups, hydrogens on the one side. Okay, so it is get links with this silicon. Now this is positively charged because one of the electron pair is used. Okay, and then of course you are having the three methyls, Me, Me, and Me. Okay, and now in that case you see this iodide has removed from here, so I can write plus I. This is actually the leaving group, and you know this I is the very good leaving group. Now this I can attack, since this is the symmetrical type of the ether. Say for example your I is attacking here. So when I is attacking here, what can happen? This bond will break in that case. Okay, and when this happens, actually you will have this structure, this one. Okay, say this is hydrogen, this is a tertiary butyl, this is oxygen linked with the silicon and three Me's. I can write it here. Okay, and then you are having this I over there along with the hydrogen, along with this tertiary butyl. So you are having this thing. Okay, now if you do the protic workup for this one, okay, if you do the protic workup, I can write H positive over there. See, the moment you do the protic workup, what can happen in that case, right? This bond, so I'm using the different color for this one. Okay, this bond will break from here, just like that. Okay, and the oxygen, actually this oxygen will grab this I, and this electron density will shift it from here. So if you see here, what would be the other product in that case? Other product would be your Me3 Si O plus I. So you are having this species, oxygen, silicon with this one and this I. This whole system actually knocked out from here, and this electron density will shifted here, and you will have only this much of a species, which is the alkene. Okay, so this is how you can go for this one. So this is the example of the anti-elimination. If you can recall, this is the example of anti-elimination. So see guys, these are the some of the reactions. Now you can do these reactions with variety of the reagents. You can use the LDA, right? You can use the DMSO, right? And you can go for, you can do the Wittig reaction. Okay, so see, however, the length of the video has increased so much, so I am not going into the details further details, but I will make a separate video how actually the LDA will do the reaction, how actually say DMSO will do the reaction. Okay, and how the Wittig halide can do this particular reaction. I'll do this reaction in the separate part also. This is the part 1 for this one, and I'll continue with the part 2. So that's it for today guys. Okay, thank you very much.